when we first started learning about fractions or rational numbers, we learned about the idea of putting things in lowest terms. So if we saw something like 3/6, we knew that 3 and 6 share a common factor. We know that the numerator, well, 3 is just 3, but that 6 could be written as 2 times 3. And say, since they share a common factor, the 3 in this case, we could divide the numerator by 3 and the denominator by 3. Or we could say that this is just 3 over 3, and they would cancel out. And in lowest terms, this fraction would be 1/2. Or, just to kind of hit the point home, if we had 8 over 24. Once again, we know that this is the same thing as 8 over 3 times 8, or this is the same thing as 1 over 3 times 8 over 8. The 8's cancel out, and we get this in lowest terms as 1/3. The same exact idea applies to rational expressions. These are rational numbers. Rational expressions are essentially the same thing, but instead of the numerator being an actual number and the denominator being an actual number, they're expressions involving variables. So let me show you what I'm talking about. Let's say that I had 9x plus 3 over 12x plus 4. Now this numerator up here, we can factor it. We can factor out a 3. This is equal to 3 times 3x plus 1. That's what our numerator is equal to. And our denominator, we can factor out a 4. This is the same thing as 4 times 3x. 12 divided by 4 is 3. 12x over 4 is 3x. Plus 4 divided by 4 is 1. So here, just like there, the numerator and the denominator have a common factor. In this case, it's 3x plus 1. In this case, it's a variable expression. It's not an actual number, but we can do the exact same thing. They cancel out. So if we were to write this rational expression in lowest terms, we could say that this is equal to 3 over 4. That's equal to 3 over 4. Let's do another one. Let's say that we had x squared. Let me see a good one. So let's say we had x squared minus 9 over 5x plus 15 over 5x plus 15. So what is this going to be equal to? So the numerator, we can factor. It's a difference of squares. We have x plus 3 times x minus 3. And in the denominator, we can factor a 5 out. So this is 5 times x plus 3. So once again, common factor in the numerator and in the denominator, we can cancel them out. But we touched on this a couple of videos ago. We have to be very careful. We can cancel them out. We can say that this is going to be equal to x minus 3 over 5. But we have to exclude the values of x that would have made this denominator equal to 0, that would have made the entire expression undefined. So we could write this as being equal to x minus 3 over 5, but x cannot be equal to negative 3. Negative 3 would make this 0, or it would make this whole thing 0. So this and this whole thing are equivalent. This is not equivalent to this right here, because this is defined at x is equal to negative 3, while this isn't defined at x is equal to negative 3. So to make them the same, I also have to add the extra condition that x cannot equal negative 3. And so likewise, over here, if this was a function, if this was, let's say this was, we wrote y is equal to 9x plus 3 over 12x plus 4, and we wanted to graph it. When we simplify it, the temptation is, oh, well, we factored out a 3x plus 1 in the numerator and the denominator. They cancel out. The temptation is to say, well, this is the same graph as y is equal to the constant 3/4, which is just a horizontal line at y is equal to 3/4. But we have to add one condition. We have to exclude the x values that would have made this thing right here equal to 0. And that would have been 0 if x is equal to negative 1/3. If x is equal to negative 1/3, this or this denominator would be equal to 0. So even over here, we'd have to say x cannot be equal to negative 1/3. That condition is what really makes this is what really makes that equal to that. That x cannot be equal to negative 1/3. Let's do a couple more of these. And I'll do these in pink. Let's say that I had x squared plus 6x plus 8 over x squared plus 4x. Or actually, even better. Let me do this a little bit. X squared plus 6x plus 5 over x squared minus x minus 2. So once again, we want to factor the numerator and the denominator, just like we did with traditional numbers when we first learned about fractions and lowest terms. So if we factor the numerator, what two numbers, when I multiply them, equal 5, and I add them, equal 6? Well, the numbers that pop into my head are 5 and 1. So the numerator is x plus 5 times x minus 1. And then our denominator, two numbers, multiply negative 2, add them, negative 1. Negative 2 and positive 1 pop out of my head. This is a positive 1, right? X plus 5 times x plus 1, right? 1 times 5 is 5. 5x plus 1x is 6x. So here we have a positive 1 and a negative 2. So x minus 2 times x plus 1 times x plus 1. So we have a common factor in the numerator and the denominator. These cancel out. So you could say that this is equal to x plus 5 over x minus 2. But for them to really be equal, we have to add the condition. We have to add the condition that x cannot be equal to negative 1. We cannot, because if x is equal to negative 1, this is undefined. We have to add that condition because this by itself is defined at x is equal to negative 1. You could put negative 1 here and you're going to get a number. But this is not defined at x is equal to negative 1. So we have to add this condition for this to truly be equal to that. Let's do some more work with rational expressions. So let's say I had a squared plus 2ab plus b squared, and all of that is over ab squared minus a squared b. And we're going to take this and divide it by, a plus b. Divided by a plus b. So the first thing we might want to do is just factor this numerator and this denominator. And then we could divide, or actually we could go the other way. We could divide and then factor. So if we divide and then factor, we could say, well, this is the same thing. This is equal to this whole expression. Let me just copy and paste it. That's probably the easiest thing to do. Let me copy and then paste it. It's equal to that expression times the inverse of this. If I divide by something, that's the same thing. That's the same thing as multiplying by the inverse, as multiplying by 1 over a plus b. And this is just going to be the same thing as that with a plus b in the denominator, because your numerator is going to be that times 1, which is just that. Your denominator is going to be ab squared minus a squared b times a plus b. So that times a plus b. So this would be a legitimate answer, but I have a suspicion that this can be further simplified. So let's see if we can simplify it. So our numerator here, a squared plus 2ab plus b squared, you might recognize that. That is a perfect square. That is our numerator. Let me color code it. So that numerator right there, that is the same thing as a plus b squared, or a plus b times a plus b, because you have a squared, you have a b squared, and then you have 2 times a and b right in the middle. That is a perfect square. Multiply it out if you don't believe me. So that numerator is that right there. And then the denominator, what is this? Well, let's see what happens if we factor out an ab down here. So let's factor out an AB. So AB squared divided by AB, A cancels out. You're just left with AB, right? AB times B is AB squared. And then minus A squared B divided by AB is just A, is just an A. This right here is the same thing as that. And you could multiply it out. AB times negative A is negative A squared B. You got that right there. So multiply it out, you should get this right there. And of course, you also have your A plus B sitting here. Now, we have an A plus B squared in the numerator. We have an A plus B in the denominator. We could say A plus B to the first power. And then we know our exponent rules here. We can just essentially cancel out an A plus B in the numerator and the denominator, which decrements this exponent by 1. So this just becomes a 1. And then this becomes a 0, or it cancels out. And so we get this is being equal to A plus B over AB over AB times B minus A, with the caveat, because we canceled this thing out in the denominator, we have to say, look, this thing can still not equal 0, because this will still make this expression undefined. We have to say the only way that this is going to be equal to 0 is if we subtract b from both sides. A is equal to negative b. So we have to add the caveat that a cannot be equal to negative b. We have to add this condition. And so this is our answer. Let's do another one. Let's say let's say we can do let's do a more involved one, just to really get our juices flowing. Let's say we have x squared plus 8x plus 16 divided by or over 7x squared plus 9x plus 2 divided by 7x over 4 over x squared plus 4x. So what is this going to be equal to? So here we could divide first. That's the same thing as multiplying by the inverse of this thing. But just for fun, let's factor these two, the numerator and the denominator here. So this numerator over here, that's pretty straightforward. That is a perfect square. That is x plus 4 squared. 4 times 4 is 16. 4 plus 4 is 8. So our numerator is x plus 4 squared. And then our denominator, what does that become? Here we're going to have to do a little bit of grouping. We're going to have to do a little bit of grouping to factor that out. So we have 7x squared plus 9x plus 2. We have to find two numbers. When I multiply them, I get 7 times 2, which is equal to 14. And when I add them, a plus b need equal 9. And the easiest two numbers are 7 and 2. So let's rewrite this. This is the same thing as 7x squared. I'll group the 7x with the 7 because they have a common factor of 7. Plus 7x plus 2x plus 2. Put parentheses around there so you can see the grouping. Factor out a 7x over here. You get 7x times x plus 1. Plus, factor out a 2 here. 2 times x plus 1. And you get the 7x plus 2. 7x plus 2 times your x plus 1. We're undistributing that expression. So this is our denominator right there. This is our denominator. So, and actually, I just realized that I made a slight error when I wrote down this problem. The numerator here is actually 7x plus 2. Lucky for us. Obviously, this is going to lead to interesting things later on, potentially. So let's see what we get. And actually, I think there's a typo here. I think this is supposed to be a 4x. Sorry, just a 4. So let me just put it like that, just in case that is a typo, because I think it's going to make it more interesting. So that's our original problem. We haven't messed with this part yet, so it won't change any of our math. But so far, we factored this bottom part. We factored this bottom part using grouping as 7x plus 2 times x plus 1. And so this expression is the exact same thing as this expression over here. And we're going to divide it by that expression. So dividing by that expression, that is the same exact thing as multiplying by the inverse of this expression. By the inverse of this expression. Oh, actually, you know what? I just realized that it was an x squared plus 4x. I just saw the problem. That is an x squared plus 4x. So this was the original problem. Sorry for all of that, but we haven't done any work here, so it's all cool. So this right over here, multiplying by the inverse of this, we multiply. Dividing by this is the same thing as multiplying by the inverse. So we just flip the numerator and the denominator. So x squared plus 4x over 7x plus 2. And then another thing we can do, let's see, if we look at this up here, we can factor out an x. So this right here, if we factor out an x, is the same thing as x times x plus 4. So if we do all of the multiplication, what does our numerator become? We have x, let me do it in a new color. We have x plus 4 squared times x plus 4. That is our numerator. And our denominator is 7x plus 2 times another 7x plus 2 times an x plus 1. So here nothing is canceling out, but we have the same term being multiplied multiple times. X to the 4th squared times x to the 4th to the first power. This is going to be equal to, we still have our x out front, so it's x times x plus 4, we could say to the 3rd power. All of that over, we have 2 7x's plus 2, so 7x plus 2 squared times x plus 1. And we are done.
In this expression, we're dividing this 3rd degree polynomial by this 1st degree polynomial. And we could simplify this by using traditional algebraic long division. But we're going to cover in this video is a slightly different technique, and we call it synthetic division. And synthetic division is going to seem like a little bit of voodoo in the context of this video. In the next few videos, we're going to think about why it actually makes sense, why you actually get the same result as traditional algebraic long division. My personal tastes are not to like synthetic division because it is very, very, very algorithmic. I prefer to do traditional algebraic long division, but I think you'll see that this has some advantages. It can be faster, and it also uses a lot less space on your paper. So let's actually perform this synthetic division. Let's actually simplify this expression. Before we start, there's 2 important things to keep in mind. We're doing kind of the most basic form of synthetic division. And to do this most basic algorithm, this most basic process, you have to look for 2 things in this bottom expression. The first is that it has to be a 1st degree, it has to be a polynomial of degree 1. So you have just an x here. You don't have an x squared, an x to the 3rd, an x to the 4th, or anything like that. The other thing is that the coefficient here is a 1. There are ways to do it if the coefficient was different, but then our synthetic division we'll have to add a little bit of bells and whistles to it. So in general, what I'm going to show you now will work if you have something of the form x plus or minus something else. So with that said, let's actually perform the synthetic division. So the first thing I'm going to do is write all the coefficients for this polynomial that's in the numerator. So let's write all of them. So we have a 3, we have a 4, it's a positive 4. We have a -2, -2, and a -1, and a -1. Then, and you'll see different people draw different types of signs here depending on how they're doing synthetic division, but this is the most traditional. And you want to leave some space right here for another row of numbers. So that's why I've gone all the way down here. And then we look at the denominator. And in particular, we're going to look whatever x plus or minus is right over here. So we'll look at right over here, we have a positive 4. Instead of writing a positive 4, we write the negative of that. So we write the negative of that, which would be -4. We write -4. And now we are all set up, and we are ready to perform our synthetic division. And it's going to seem like voodoo. In future videos, we'll explain why this works. So first, this first coefficient, we literally just bring it straight down. And so you put the 3 there. Then you multiply what you have here times the -4. So you multiply it times the -4. 3 times -4 is -12. Then you add the 4 to the -12. 4 plus negative 12 is negative 8. Then you multiply negative 8 times the negative 4. I think you see the pattern. Negative 8 times negative 4 is positive 32. Now we add negative 2 plus positive 32. That gives us positive 30. Then you multiply the positive 30 times the negative 4, and that gives you negative 120. Negative 120, and then you add the negative 1 plus the negative 120, and you end up with a negative 121. And now the last thing you do is you say, well, I have one term here, and in this plain vanilla simple version of synthetic division, we're only dealing actually when you have x plus or minus something, so you're only going to have one term there. So you separate out one term from the right, just like that, and we essentially have our answer, even though it seems like voodoo. So to simplify this, you get, and you can have a drum roll right over here. This is going to be, this right over here, this is going to be the constant term. You could think of it as a degree 0 term. This is going to be an x term, and this is going to be an x squared term. You can kind of just build up from here, saying this first one's going to be constant, then this is going to be an x term, then an x squared. If we had more, you'd have an x to the third, an x to the fourth, so on and so forth. So this is going to be equal to 3x squared minus 8x plus 30, and this right over here you can view as the remainder. So minus 121 over the x plus 4. This didn't divide perfectly, so over the x plus 4. Another way you could have done it, you could have said this is the remainder, so I'm going to have a negative 121 over x plus 4, and it's going to be plus 30 minus 8x plus 3x squared. So hopefully that makes some sense. I'll do another example in the next video, and then we'll think about why this actually works. Let's do another synthetic division example. And in another video, we actually have the why this works relative to algebraic long division. But here it's going to be another, let's go through the process of it just so that you get comfortable with it. And now is a good chance to give it a shot, to actually try to simplify this rational expression. So let's think about this step by step. So the first thing I want to do is write all of the coefficients of the numerator. So I have a 2, I have a 2, I have to be careful here, because the 2 is a coefficient for x to the 5th. I have no x to the 4th term. So for the x to the 4th term, I'm going to, let me start over. So I have the 2 from 2x to the 5th, and then I have no x to the 4th, so it's really 0x to the 4th. So I'll put a 0 as the coefficient for the x to the 4th term. And then I have a negative 1 times x to the 3rd. And then I have a positive 3 times x squared. Positive 3 times x squared, negative 2 times x, negative 2 times x, and then I have a constant term or 0 degree term of 7. I just have a positive 7. And now let me just draw my little funky synthetic division operator looking symbol. And remember, the type of synthetic division we're doing, it only applies when we're dividing by an x plus or minus something. There's a slightly different process you would have to do if it was 3x, or if it was negative 1x, or if it was 5x squared. This only works when we have x plus or minus something. In this case, we have x minus 3. So we have the negative 3 here. We have this negative 3. And the process we showed, there's other ways of doing it, is you take the negative of this. So the negative of negative 3 is positive 3. And now we're ready to perform our synthetic division. So we'll bring down this 2, and then multiply the 2 times the 3. 2 times 3 gives us 6. 0 plus 6 is 6. And then we multiply that times the 3, and we get positive 18. Negative 1 plus 18 is 17. Multiply that times the 3. 17 times 3 is 51. 3 plus 51 is 54. 54. Multiply that times 3. The numbers are getting kind of large now. So that's going to be what? 50 times 3 is 150. 4 times 3 is 12. So this is going to be 162. Negative 2 plus 162 is 160. 160. And then finally, 160 times 3 is going to be 480. 480. And you add 480 to 7, you get 487. 487. And you can think of it, I only have one term or one number to the left-hand side of this bar here, or I'm just doing the standard traditional x plus or minus something version of long division, or synthetic division, I should say. So I can separate this out, and now I've essentially gotten my answer. And it looks like voodoo, and it kind of is voodoo. That's why I don't like to do it, because you're kind of just memorizing an algorithm. But there are other videos why we explain why. And it can be fast and convenient and paper saving very often, like you see right here. But then we have our final answer. It's going to be, and let me work backwards. So I'll start with our remainder. So our remainder is 487. 487. It's going to be 487 over x minus 3. Over x, 487 over x minus 3. And so this is our constant term. And so you're going to have plus 160 plus 487 over x minus 3. Now this is our x term. So it's going to be 54x. 54x plus all of this. This is going to be our x squared term. So this is going to be 17x squared plus 54x plus 160 and all of that. Then this is going to be our x to the third term. So this is going to be 6x to the third plus all of that. And then finally, this is our x to the fourth term, 2x to the fourth. And let me erase this just because I don't want to. So then I have my x to the fourth term. So it is 2x to the fourth. And we are done. This thing simplifies to this right over here. And I encourage you to verify it with traditional algebraic long division. We already know a good bit about exponents. For example, we know if we took the number 4 and raised it to the third power, this is equivalent to taking 3 4s and multiplying them. Or you could also view it as starting with a 1 and then multiplying the 1 by 4, or multiplying that by 4 3 times. But either way, this is going to result in 4 times 4 is 16, times 4 is 64. We also know a little bit about negative exponents. So for example, if I were to take 4 to the negative 3 power, we know this negative tells us to take the reciprocal 1 over 4 to the third. And we already know 4 to the third is 64, so this is going to be 1/64. Now let's think about fractional exponents. So we're going to think about what is 4 to the 1/2 power. And I encourage you to pause the video and at least take a guess about what you think this is. So the mathematical convention here, the mathematical definition that most people use, or that frankly all people use here, is that 4 to the 1/2 power is the exact same thing as the square root of 4. And we'll talk in the future about why this is, and the reason why this is defined this way is it has all sorts of neat and elegant properties when you start manipulating the actual exponents. But what does the square root of 4, especially the principal root, mean? Well, that means, well, what is a number that if I were to multiply it by itself, or if I were to have two of those numbers and I were to multiply them times each other, that same number, I'm going to get 4. Well, what times itself is equal to 4? Well, that's, of course, equal to 2. And just to get a sense of why this starts to work out, well, remember, we could have also written that 4 is equal to 2 squared. So you're starting to see something interesting. 4 to the 1/2 is equal to 2. 2 squared is equal to 4. So let's get a couple more examples of this, just so you make sure you get what's going on. I encourage you to pause it as much as necessary and try to figure it out yourself. So based on what I just told you, what do you think 9 to the 1/2 power is going to be? Well, that's just the square root of 9, the principal root of 9. That's just going to be equal to 3. And likewise, we could have also said that 3 squared is, or let me write it this way, that 9 is equal to 3 squared. These are both true statements. Let's do one more like this. What is 25 to the 1/2 going to be? Well, this is just going to be 5. 5 times 5 is 25. Or you can say that 25 is equal to 5 squared. Now, let's think about what happens when we take something to the 1/3 power. So let's imagine taking 8 to the 1/3 power. So the definition here is that taking something to the 1/3 power is the same thing as taking the cube root of that number. And the cube root is saying, well, what number, if I had 3 of that number and I multiply them, that I'm going to get 8. So something times something times something is 8. Well, we already know that 8 is equal to 2 to the 3rd power. So the cube root of 8, or 8 to the 1/3, is just going to be equal to 2. This says, hey, give me the number that if I say that number times that number times that number, I'm going to get 8. Well, that number is 2, because 2 to the 3rd power is 8. Do a few more examples of that. What is 64 to the 1/3 power? Well, we already know that 4 times 4 times 4 is 64. So this is going to be 4. And we already wrote over here that 64 is the same thing as 4 to the 3rd. I think you're starting to see a little bit of a pattern here, a little bit of symmetry here. And we can extend this idea to arbitrary rational exponents. So what's happening? What happens if I were to raise, let's say I had, let me think of a good number here. So let's say I had 32. I have the number 32, and I raise it to the 1/5 power. So this says, hey, give me the number that if I were to multiply that number, or I were to repeatedly multiply that number 5 times, what is that? I would get 32. Well, 32 is the same thing as 2 times 2 times 2 times 2 times 2. So 2 is that number that if I were to multiply it 5 times, then I'm going to get 32. So this right over here is 2. Or another way of saying this kind of same statement about the world is that 32 is equal to 2 to the 5th power.
Simplify the expression using rational exponents. So we have the cube root of all of this stuff over here, which would be the same thing, or which is the same thing by definition, as all of this stuff, 64, a to the 6th, b to the 3rd, c to the 9th, raised to the 1/3 power. These are equivalent by definition. And if we take the product of a bunch of things and raise them to an exponent, that's the same thing as raising each of these things that we're taking the product of to the exponent first and then multiplying. So this is going to be equal to 64 to the 1/3 power times a to the 6th to the 1/3 power times b to the 3rd to the 1/3 power times c to the 9th to the 1/3 power. And we've seen this in several examples already. Well, first let's try to simplify this. 64 to the 1/3. You might recognize that already, but we can factor 64 as, well, I won't do a pure prime factorization because you'll see it's 4 to the 3rd power. Actually, you can verify that for yourself. Or I encourage you, if that's not obvious, to see that this is 4 to the 3rd power, 64. Multiply it out for yourself. Or if you're like, how did you know that? Do the prime factorization. And what you're going to do is well, let me just show you. If you do the prime factorization, you're going to have 2 times 32. 32 is 2 times 16. 16 is 2 times 8. 8 is 2 times 4. And the 4 is 2 times 2. So you can have 2 multiplied by itself 3 times. Or you could have it 2 multiplied by itself 3 times, and that happens twice. Or you could have 4 times 4 times 4. So if it immediately didn't jump in your head that 64 is 4 to the 3rd power, you can literally do a brute force prime factorization here and see that you have 6. You can factor this into 2 to the 6th power, or the same thing as 4 to the 3rd power. So I'll let you think about that a little bit. But this right here simplifies. If 64 is 4 to the 3rd power and you raise that to the 1/3 power, that is the same thing. Actually, let me write it that way. That could make it more interesting. So this right here, this is 4 to the 3rd power. So if I have 4 to the 3rd power and then that raised to the 1/3 power. So if I want to rewrite that term right over here, that's going to be 4 to the 3/3 power. I'm literally multiplying 3 times 1/3. 4 to the 3rd and then that to the 1/3. Then over here, I have a to the 6th and then that to the 1/3 power. That is going to be a to the 6 times 1/3 power, or a to the 6/3 power. Then I have b to the third, and then that raised to the 1/3. So that's going to be, we literally can multiply exponents here. So we have b to the 3 over 3 power. And then finally, we have c to the 9th, and then that raised to the 1/3 power. So that is c to the 9 over 3 power. And if you simplify it, this first term here, 4 to the 3/3, that's just 4 to the first power, so that's just 4. We have a to the 6/3. 6/3 is just 2, so that just becomes a squared. B to the 3/3 power, that's just b to the first, or b. And then finally, c to the 9/3, that's just c to the third power. So we write c to the third here. And we are done. Simplify 3a to the 5th over 9a squared times a to the 4th over a to the 3rd. Simplify the expression using
So right here, we've got 3 to the a power. So right here, we've got 3 to the a power, or 8th power, I guess, is, I don't want to confuse it with the number 8. 3 to the a power is equal to the 5th root of 3 squared. And what we need to figure out is, what would a be equal to? Let's solve for a. And I encourage you right now to pause this video and try it on your own. Well, if you have a 5th root right over here, one thing that you might be tempted to do to undo the 5th root is to raise it to the 5th power. And of course, we can't just raise one side of an equation to the 5th power. Whatever we do to one side, we have to do to the other side if we want this to still be equal. So let's raise both sides of this equation to the 5th power. Raise both sides to the 5th power. Now, this left-hand side, we just have to remember a little bit of our exponent properties. 3a to the 5th power. And if we want to just remind ourselves where that comes from, that's the same thing as 3 to the a times 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 3 to the a. Well, what's that going to be equal to? That's going to be 3 to the a plus a plus a plus a plus a power, which is the same thing as 3 to the 5a power. So the exponent property here is, if you raise a base to some exponent and then raise that whole thing to another exponent, that's the equivalent of raising the base to an exponent that is the product of these two exponents. So we could rewrite this left-hand side as 3 to the 5a power. 3 to the 5a power is going to be equal to, well, if you take something that's a 5th root and you raise it to the 5th power, then you're just left with what you had under the radical. That's going to be equal to 3 squared. So now things become a lot clearer. 3 to the 5a needs to be equal to 3 squared. Or another way of thinking about it, we have the same base on both sides, so this exponent needs to be equal to this exponent right over there. Or we could write that 5 times a needs to be equal to 2. And of course, now we can just divide both sides by 5, and we get a is equal to 2/5. 2 over 5. And this is an interesting result. And what's neat about this example, it kind of shows you the motivation for how we define rational exponents. So let's just put this back into the original expression. We've just said, or we've just solved for a, and we've gotten that 3 to the 2/5 power to the 2, and actually let me color code it a little bit because I think that'll be interesting. 3 to the 2 over 5 power, 3 to the 2 over 5 power is equal to the 5th root. Notice the 5th root. So the denominator here, that's the root. So the 5th root of 3 squared. 3 squared. So if you take this base 3, you square it, but then you take the fifth root of that, that's the same thing as raising it to the 2/5 power. Notice, take this 3, take it to the second power, and then you find the fifth root of it. Or we could, if you use this property that we just saw right over here, you could rewrite this. This is the same thing. This is the same thing as 3 squared, and then you raise that, to the 1/5 power. We saw that property at play over here. You could just multiply these two exponents. You'd get 3 to the 2/5 power, and that's the same thing as 3 squared, and then find the fifth root of it. 3 squared, and then you're essentially finding the fifth root of it.
We're asked to simplify the cube root of 27a squared times b to the fifth times c to the third power. And the goal whenever you try to just simplify a cube root like this is we want to look at the parts of this expression over here that are perfect cubes, that are something raised to the third power, that we can take just the cube root of those, essentially taking them out of the radical sign, and then leaving everything else that is not a perfect cube inside of it. So let's see what we can do. So first of all, 27, you may or may not already recognize this as a perfect cube. If you don't already recognize it, you can actually do a prime factorization and see it's a perfect cube. 27 is 3 times 9, and 9 is 3 times 3. So 27, its prime factorization is 3 times 3 times 3. So it's the exact same thing as 3 to the third power. So let's rewrite this whole expression down here. But let's write in terms of things that are perfect cubes and things that aren't. So 27 can be just rewritten as 3 to the third power. Then you have a squared, clearly not a perfect cube. A to the third would have been. So we're just going to write this. Let me write it over here. We can switch the order here because we just have a bunch of things being multiplied by each other. So I'll write the a squared over here. B to the fifth. B to the fifth is not a perfect cube by itself, but it can be expressed as a product of a perfect cube and another thing. B to the fifth is the exact same thing as b to the third power times b to the second power. And if you want to see that explicitly, b to the fifth is b times b times b times b times b. So the first three are clearly b to the third power, and then you have b to the second power after it. So we can rewrite b to the fifth as a product of a perfect cube. So I'll write b to the third. I'm doing that same purple color. So we have b to the third power over here. And then it's b to the third times b squared. So I'll write the b squared over here. And we're assuming we're going to multiply all this stuff. And then finally, we have, I'll do it in blue, c to the third power. Clearly, this is a perfect cube. It is c cubed. It is c to the third power. So I'll put it over here. So this is c to the third power. And of course, we still have that overarching radical sign. So we're still trying to take the cube root of all of this. And we know from our exponent properties, or we could say from our radical properties, that this is the exact same thing. That taking the cube root of all of these things is the same as taking the cube root of these individual factors and then multiplying them. So this is the same thing as the cube root. And I could separate them out individually, or I could say the cube root of 3 to the third, b to the third, c to the third. Actually, let's do it both ways. So I'll take them out separately. So this is the same thing as the cube root of 3 to the third times the cube root. I'll write them all in. Well, let me color code it so we don't get confused. Times the cube root of b to the third times the cube root of c to the third times the cube root. And I'll just group these two guys together just because we're not going to be able to simplify it anymore. Times the cube root of a squared, b squared. I'll keep the colors consistent while we're trying to figure out what's what. A squared, b squared. And I could have said that this is times the cube root of a squared times the cube root of b squared, but that won't simplify anything. So I'll just leave these like this. And so we can look at these individually. The cube root of 3 to the third, or the cube root of 27, well, that's clearly just going to be, I want to do that in that yellow color. This is clearly just going to be 3. Right? 3 to the third power is 3 to the third power, or it's equal to 27. This term right over here, the cube root of b to the third, well, that's just b. That's just b. And the cube root of c to the third, well, that is clearly, I want to do that in that is clearly just c. So our whole expression has simplified to 3 times b times c times the cube root of a squared b squared times the cube root of a squared b squared. And we're done. And I just want to do one other thing, just because I did mention that I would do it. We could simplify it this way, or we could recognize that this expression right over here can be written as 3bc to the third power. That if I take three things to the third power and I'm multiplying it, that's the same thing as multiplying them first and then raising to the third power. It comes straight out of our exponent properties. And so we can rewrite this as the cube root of all of this times the cube root of a squared b squared. And so the cube root of all of this, of 3bc to the third power, well, that's just going to be 3bc, and then multiplied by the cube root of a squared b squared. I didn't take the trouble to color code it this time because we already figured out one way to solve it. But hopefully that also makes sense. We could have done this either way. But the important thing is that we get that same answer.